Hi, everybody. I hope you all had a good spring break, either relaxing or catching up with the material that was piling up during the first part of this course. So we are back to continue with our discussion on identification methods. We are going to cover some material today. We're going to have fun actually doing real exercises together where we're going to see how to use some of these methods with data, mostly manufactured, but nonetheless realistic. So next lecture on Wednesday is going to be a review of what we have covered already in the first two parts of this course, which was mainly an undergraduate material that gave a quick overview of things related to standard controller design theory in continuous and discrete time. So we're going to cover that, and I'll assign the exam at the end of the week, so you can have several days, a few days to go to do it. Okay. So let me turn off the camera then, share my screen, and get going with our lecture. What we are covering in this section, which is in the PDF identification lecture notes and for spring 2024, what I'm covering here is what the title suggests, namely identification of dynamic systems. So the term is highly descriptive of what it refers to, namely, we try to identify how a dynamic system behaves. Why do we want to do that? Well, for a number of reasons. One could be controller design, which is classic, but there may be more things that are useful. We may want to use this model for simulation. This is not just to play with a process. For quite some time, in the last 2-3 decades, I would say, simulation is an integral part of whatever engineering design one is dealing with. Namely, you have a design, then you test it on the computer by looking at several scenarios, and you try to make sense out of what the simulations tell you. So a simulation needs a model. A model, as we have said several times, is never a perfect description of a system. It's useful enough so it can answer questions about the system. Also, a model can be very useful to train operators by simulation. It's done routinely in the chemical industry. It's done in other industries. If you have any friends who are commercial pilots, you know that they have to take simulator training every now and then in an actual mechanical / computerized simulator. Also, what in the past used to be controller design methods based on a methodology that said first you do A, then you do B, then you do C, and then you do D, and you have your controller, gradually has been complemented. This explicit design methodology has been complemented by pure trial and error, because trial and error these days can do a lot. You can just try a gazillion of controllers on your model, see which one behaves best, and pick that one. Interestingly enough, people were talking about these things in the 90s already. Computers were powerful enough to be able to do these things. We've seen a few of these things already. We saw how to do simulation, how to solve differential equations. Differential equations, you can solve them in a number of ways using sophisticated software, but in the simplest possible case, even if you have multiple differential equations for a forward integration problem, you can use Euler's method, right? Which is an extremely simple idea. Euler knew that 3 centuries ago. He just didn't have computers. Now that we have computers, we can say y prime at any point is approximately equal to y at point t plus delta t minus y of t divided by delta t, and we proceed to solve the equations easily forward. We saw that already. So in the first part of this identification section, again, we are trying to build models. In fact, we try to build dynamic models. Dynamic models that are useful. So we want to build dynamic models that are useful for these things that I mentioned. I'll emphasize for the umpteenth time, they will never be perfect, but they shouldn't have imperfections that may be fatal. We already have seen what imperfections may be fatal. If a model can have the wrong sign of the steady state gain, it cannot be used for good control, for control with integral action, that is, because it will push the plant in the opposite direction. Example, if you have an AC, you must know that when the AC is on, the temperature goes down. Eventually, the steady state gain is negative. If you think it's positive, good luck, you'll never get anything. All those things set the stage for what we do in this identification section. And we have seen some nuts and bolts with simple methods. We saw that if you have a first order system, you make a step change in the input of your system, you look at the output, you look at this over that, and these two give you a ratio K, which is the steady state gain. You take 63% of the total response and you go from here to here. This is one time constant, so you can easily do these things for a first order system. You can have first order system plus time delay. It's the standard equation, the transfer function rather, that we have seen several times. So again, you may make a step change like this. You'll get a response for your process that is something like this. You approximate it by first order plus time delay. This is the time constant from here to here. Sorry, the dead time from here to here. At 63%, you get the time constant tau. So make it a little nicer. This is theta. This is tau. And then, of course, this over that give you the gain K of the processes. And even if you have second order systems, if they are overdamped, you go back and you approximate them like this. If they are underdamped, and for this kind of change, you may get something like this. There are ways to get the overshoot this over that, or the damping factor this over that. And of course, you get the gain always by dividing those two, so you can easily get these models. These kinds of models are easy to get. When you do dedicated experiments, you can apply these simple methods. People actually do it as an initial guess, perhaps, or sometimes even as the final guess. The only thing is that there is noise in all of these responses. So the true response of a system is not like the red lines that I have shown here, but they may be like this, or like that, or like this. And if you try to get the 63%, for example, okay, so where is the 63%? Is it, let's say here, or is it here? You may be a little bit above or below, right? Depending on noise. So it's a good idea to try to do what you would do with eyeballing. And let's say if you start with this green data set, you can eyeball the response by a red curve. You can take your pen and draw the red curve. Or you can draw this blue curve, or you can do this red curve. That's exactly what statistics does. Okay, statistics makes that task easy. So it all starts, of course, perhaps in the most interesting case, in the simplest and yet interesting case of a model Y depends on X. It's a static model, and a human would say That's the line that I can draw nicely by eyeballing this. Well, regression actually finds what is y as a function of x. As a matter of fact, these days there's a lot of discussion about machine learning or artificial intelligence. Well, this thing, drawing a straight line by doing calculations, is in a certain sense what one would call artificial intelligence, but it's been around for at least 2 centuries, so it doesn't impress us very much. Actually, when it first came out, it impressed people tremendously because Gauss, when he figured it out, he took points and he fit a curve, and then he predicted the next point when the asteroid Ceres would be seen. It was utterly impressive that he could do that. In fact, others had tried very hard to solve this problem. It wasn't easy. Euler himself had failed. He came close to solving it. He figured out what would have to be done. Well, Gauss actually did it. And it was so impressive, people were thinking that maybe Gauss had to resort to sorcery to get such a result and all kinds of folklore-related stories, but I'll stop here and move on. So it's the same idea where calculations, and we'll see in a second these calculations, which you have seen before, but I'll mention it to be complete. Calculations can be used to do something that the human eye does effortlessly, right? You can easily draw a straight line that goes through the points in a somewhat balanced way. Well, calculations can actually do this very well. A lot of what AI can do these days relies on this very simple idea. It minimizes the sum of squared errors, and it actually fits a function to minimize that sum of squared errors, the errors being what the function has as an output and what the measurement say. You can do that for regression or classification. The secret sauce, what makes a difference here, is what is the form of that function. Straight line is easy, I can write it down, okay? What is a function, though, to which I give pixels, and the function tells me whether this is a cat or a dog or nothing else, or something else. It's much, much more difficult. The magic function shape recently was found to be deep learning neural networks, which have a certain structure inspired by how the brain is structured and all that, and that's a subject for another course. Going back to this, in section 2 of the notes, we're talking about parametric methods, again, as I started saying, so that we can do all of these things. What things? From the green line here, draw the red line, or from the green data here, draw the blue, the red or the blue line, or from the green data here, draw the red line. All that can be done in a reasonably good fashion using statistics, and in particular, the method of least squares. I'll mention early some caveats because they're very important, and despite that, they're frequently forgotten. Least squares works very well to minimize the effect of noise on the parameters, the parameter estimates, that is, so that you can find your B0 and B1 very well when you have a model that is reasonably realistically structured. If the model structure is not reasonable, least squares will still give you something, but it may not be very good. Example. You have these data points, right? Well, you can eyeball this and say this is a curve. This is all static. Forget about dynamic for a moment. This is all static model. Well, least squares will fit a line for you. If you give such data to Excel, it will fit a nice straight line. Okay? And if there is plenty of noise, you'll actually get a nice, good R square. Of course, you have to continue and look at what we call the residuals. So the data points this and this and this and this and this and this. How much is left out by this fit? Well, you can clearly see a pattern, right? It goes like this, and then it goes up, and then it goes like this. There's clearly a pattern here in what are called the residuals. What are the residuals or residual errors? To be complete, people usually don't mention errors, they just say the residuals. The residual is red minus blue, red points minus blue, namely the actual measurement minus what the model spits out as an output. There's a pattern here, so something was left out. The model isn't very good. It's much more difficult to discern these things when you have dynamic models because it's not a nice, simple, clean picture. It's more interesting. But more about this in a second. So let's take things one at a time. We're still in section 2 at the very introduction. This is not a course on regression. Some of you may have taken actually experimental methods this semester. So we had a 3-lecture review regression there, which was more extensive. It would be ideal if one could take an entire course on these methods because they have tremendous usability and they're very widely used. And one can easily make mistakes, not in the calculations. The calculations will be correct. It will be the interpretations of what the calculations mean. And we'll have such things as we go along. I'll show you a number of these misinterpretations of actual data. So in this section 2, I have example 3 that says linear and nonlinear regression. Let's clarify what that says. If I have a function y that depends on u, and let's say for a moment that it's a static model to keep things simple. So y is a function of u, and there are some parameters here in this model. So you have u, your input, you have the output, and here is model that you try to identify. You can estimate the parameters theta by linear regression or linear least squares. Usually the two terms are synonymous. They mean the same thing, so they're about the same. Incidentally, regression comes historically from a study that Sir Francis Galton did. Galton was Darwin's cousin, so both were noblemen. They had plenty of money to spend around. Very, very thankfully for science and statistics, they spent it on very scientific endeavors, so they left a good legacy. So Galton figured that if you have variables that are not very well correlated, then like two parents that have a certain height and they have children, the height of the children in the next generation, on average, regresses to the mean. So that was the famous regression to the mean that he discovered experimentally based on data. And he had a statistic, a certain method to fit a straight line. So the method is called regression, and we are stuck with that for a long time. Everybody understands it, so there is no point in changing right now. So regression basically means least squares, although there are other ways to minimize errors, like least absolute error, or actually there is an entire category these days with various properties. More about that later. Let's stick to linear regression on least squares. When is regression linear? A regression problem is linear if this function f of u and theta is linear in theta. The effect of u on y could very well be nonlinear. So u acting on y could very well be nonlinear. And we have given the formal definitions of linear and nonlinear functions, but it's fairly simple to state it in words which humans understand better, perhaps. So a function is linear when you make it with respect to an input. So if you make a change, the output changes. You double the change, the output doubles. You triple, the output triples, and so on. Or you take two inputs, the sum of two inputs creates an output, which is the sum of the two outputs. Okay, so this is linearity. A function is linear in theta if these properties hold, and if f, that function, is linear in theta, the regression problem is linear. Let's see examples. So a straight line is obviously a theta 0 plus theta 1x. Is this effect or u? Let's make it u. Is the effect of u on y linear? Yes. Is the parameter theta, which is a vector in general. In this case, it's theta 1, theta, or theta 0. Theta 1. Is this linear? Is this right-hand side f of u and theta linear? Yes, check, check. Okay, this is a linear regression problem. I can estimate theta 0, theta 1, linear regression. Why do I care? Because linear regression is a lot easier to handle, both numerically and analytically. I can derive nice properties, nice statistics. I can write formulas. Actually, these days, the landscape of is getting a little changed because you can do a lot of that stuff also very easily numerically by intensive computer calculations, but nevertheless in realistic time. So this landscape is changing. We'll talk about that in a second. Let's see another example. Y is equal theta 0 plus theta 1 e to the minus u. Is this a linear regression problem? Well, let's see. The parameters appear linearly. Fu theta is linear in theta, right? It's a linear function. It's theta 0 times 1 plus theta 1 times something. As a function, this right-hand side is linear in theta, in the components of this vector. Is the effect of u on y linear or nonlinear? It's clearly nonlinear, right? Because of the exponential. I can change u, y will change by something. Double the change in u, you are not going to get double the change in y, right? You can get several of these linear regression equations. Here's a classic one. That's typically the equation for a thermocouple. You may have seen this. People have figured out that for the limited range, you can connect temperature to the voltage or current generated by thermocouple by this. Is this linear regression? Yes. Is the effect of u on y non-linear? Yeah, it's non-linear. Okay, it's non-linear here. Of course, a regression itself may be nonlinear. Here's a classic one. This is an equation you have seen before in your undergraduate years. This is an equation that connects. Does this remind you of anything you've seen in your reaction engineering kinetics course? If U is temperature and this is reaction rate. What equation is that again? Yeah, it's the Arrhenius equation. The Arrhenius equation is a nonlinear regression equation. What does that mean? It means that the right-hand side here, which is f of u and theta, is nonlinear in the parameters, nonlinear in the parameters theta, right? So if I try to solve least squares, I have to use numerical methods. It's not easy to get analytical solutions for nonlinear regression equations. Plus, if I want to do statistics, I can do these by computer-intensive methods, but not easily by formulas that are explicit. So let's see very quickly again how we fit a straight line, and we'll go very quickly because this is something we've seen before. So I just want to emphasize what is important, not the mechanics, which I'm pretty sure you've seen before. So example 4 in section 2.2, and the notes gives a quick introduction to linear least squares. So it's a straight line case, y equals ax plus b, or let's write it in the typical fashion, beta 0 plus beta 1x, or sometimes theta 0 plus theta 1x. By the way, it's a typical thing in today's jargon. For linear regression to use betas, for nonlinear regression you use thetas. And if you just want the utmost simplicity, you just use letters without indices. Okay, the 0 and 1 instead of starting at 1 and then at 2 is because typically people don't care too much about this beta 0 because it's what people call the bias term. So it's essentially the 0 of your measuring scale. If you measure temperature in Fahrenheit or temperature in Celsius, you'll get a different beta 0 there as the effect of, say, heat rate on temperature. But the important part is what is beta 1? What is the effect of heat rate on temperature? So people worry about beta 1, and then there may be typically more of these terms around, maybe x squared, exponential size, so on and so forth. So how does linear regression work here? Well, example 4 summarizes it very quickly. So let's summarize that very quickly because it's something you've seen before. So you have here y, you have x, you have all of these data points. This is x1, this is x2, all the way through the point xp, and you want to build this line here. You have the vector x is x1 through xp. You have the vector y, vector, which are your measurements. And the idea is you want to make exactly the errors as much as possible. And of course, the reason why you want to do this exercise is your model structure is this, but this is what we call a model structure, right? The actual measurements yi are a random, rather are values of a random variable which depends on xi, the point xi, where I goes from 1 to p. And how does yi depend on xi? Well, it depends as follows. Beta 0 plus beta 1, plus there is an error here. Okay. And unfortunately, you don't know that epsilon I, and you can only measure this, and you assume this to be known exactly. There are methods when this is not known exactly, but that's okay for now. Let's assume that this is known exactly. So you're going to get then all of these y1 essentially is beta 0 plus beta 1 x plus epsilon 1 all the way beta 0 plus beta 1 xp plus epsilon p. Unfortunately, you don't know these epsilons. This is noise, so you don't know this. The only thing that you know is this. Let's put it in another color. It's what you measure. So you can measure this. You can measure all of these until you're here. And of course, you know your xi's. The question is then, how can you find the parameters beta 0, beta 1? Well, you create the errors. What is the error? Well, the error at the point I, at the point xi, is defined as the measurement, the thing that you just measured, minus what your model structure produces. So your model produces beta 0 plus beta 1 x. If those are the true values, you don't know them yet. So I'm going to be a little bit pedantic and strict, but just want to emphasize that you don't know these yet. Okay, this is your structure. So you want all of these errors to be small. So you want y1 minus beta prime 0 plus beta 1 x1 to be small. You want y2 minus beta 0 plus beta 1 prime x2 yp minus beta prime 0 plus beta px, sorry, 1xp. You want all of these to be small. Well, you could ask all of these to be equal to 0. Unfortunately, you cannot do that, right? You can make all of these equal to 0 because you have p equations and how many unknowns to fit here? the two unknown parameters, right? So you try to make those. Small one idea then might be to take the sum all of these plus this plus this plus to make the sum of all of these small. That wouldn't be a great idea either, right? Why? Why would it not be a great idea to find beta 0 and beta, to estimate beta 0, beta 1 by taking the sum of the errors? Take a perfect case. Well, let's say I fit this line, right, to these data points I have here. And they are on a perfect straight line. So this error is equal to that error with a minus sign. This is equal to this. And let's make it nice and clean. So this cancels that, and this cancels that. So the sum of the errors is 0, right? Cannot be better. So this line fits the data perfectly, not quite. It's completely out of the question. The thing is that you want to avoid positive and negative errors, which can be done in a number of ways. You need to make the magnitude of the errors small, not the errors, the actual values. One way to capture the magnitude of the errors would be to take the absolute values, right? This makes the magnitude, qualifies as magnitude of the error. Actually, interestingly enough, that's what people in the 18th century considered, in the 18th century, yes, considered first, the absolute values, which is more difficult to solve. Today it can be solved very easily because you can convert it to a linear programming problem on the computer. So it's solvable trivially. But mathematically, you cannot analytically find the solution. Then people figured, well, let's make those squares. Now the squares are differentiable everywhere, unlike the absolute value, because the absolute value is this function, right? X, and this is absolute value, not X, let's say eta in general. The absolute value has a discontinuity in the derivatives there, right? So if the derivative here is positive, the derivative here is negative, it's a mess. It's difficult to solve this problem. Solve it. The squares, nice and clean. If you have eta square, it's, let me use another color. Eta square, this is your beautiful eta square, nice and clean, simple. That's the main reason why Gauss invented least squares. The best part is that it's simple and easy. That was his biggest reason for choosing it. So you take the sum of these, and what do you do with the sum? You want to minimize it, right? You want to minimize this with respect to beta 0 prime, beta 1 prime. That's the least squares. It turns out that the minimization here can be done very easily. And you know the analytical solutions, they're in calculators, even in watches these days, they are powerful enough so that you can do least squares on your watch. But the interesting thing with linear least square is that if you take an approach based on vector matrix notation, you can get more. It's not just to be fancy, it's that you can get more. Let's see what more you can get. First of all, this thing here, this expression, I can write, and it's very easy to show that. Let me see how I can write it. So this expression here turns out to be the norm of the following vector. It's the vector y1 all the way to yp minus this beta 0 plus beta 1 all the way beta prime 0 plus beta 1 xp. So this vector is the error vector. Okay, that's how I define the error vector. And the norm of the error vector squared, which is defined as E transpose E, which, let's see, well, it's actually this thing here, this sum of the squares. So essentially, I'm trying to minimize this by selecting beta prime 0, beta prime 1. But for this vector E, I can do more. I can write this as, so let me put it here, yp minus a matrix times the parameters. Can you help me with what I need to put here in this matrix X? So when I multiply this matrix X times this vector beta prime, I will get this vector that I have up here. What should be in the first line? So if I multiply this by that, I get this number. Yes, 1x1. And obviously the second line will be 1 plus x2, going, would be 1xp, the last line, right? This is a nice representation of the problem. Of course, for now you may ask, why on earth do I care? Well, because you can get two interesting things. One is you can get the optimal values for beta 0, beta 1. You can get the values that minimize the sum of the squared errors, that minimize this, the sum of the squared errors. So if I put that in here, I get that the optimal values, which typically are denoted by hat. Okay. So this is my vector. That the values of these, which minimize the sum of the squared errors, are given as a solution of the equation x transpose x times this vector beta hat is equal to x transpose y. And this has a nice interpretation as sometimes they're called the normal equations, or the normal equation in matrix form. It has nice geometric interpretations about subspace and all that. We'll discuss those at another time. So this is fine. You write the solution in vector matrix form, but you could also do it element by element and say beta 0 hat is this. It's a fraction which you can do on your own, and I give it in the notes. Beta hat 1 is that, this vector, and it's in the notes as well. But there is more to that. What you can get here in addition to this thing is the variance of this estimator beta hat, or I have it in the notes as theta hat in general. What is the variance of an estimator? First of all, let's understand why we have a distinction between estimate and estimator. It's an easy concept, but one has to be careful and vigilant, because sometimes language may slip and we may misunderstand, and with experience, of course, you can get the right interpretation from it, from the context, but nevertheless, let's be careful here. So estimate, what is an estimate? It's the actual value of the vector beta hat that you just estimated. So this is numbers. So this is an element of R2. It's a vector that has two components. So let me, by definition, this is beta hat 1, sorry, 0, beta hat 1. Okay. So an estimate is numbers, specific numbers. An estimator is a random variable. So estimator versus estimate, a random variable. In what sense is this a random variable, beta capital hat or B hat? Well, if I do an experiment and collect values at these points, x1, x2, all the way through xp, I can collect these values and I fit a straight line and I get this straight line. If I collect values again, I'm not going to, at the same points, I'm not going to get the same values. I'm going to get somewhat different values. Maybe like this. So we're going to get a slightly different slope, right? It's not going to be very far, but it's going to be slightly different. And if I do the experiment again, I'll get yet another set of values at these points, and I'll get this line perhaps, okay? All of these lines are going to be close to each other, but they are going to be in general different. Different in one way. In what way? Well, the estimate for the blue data is going to be beta hat 0, beta hat 1. The estimate for the green data is going to be beta hat 0, beta hat 1. The estimate for the, I should use black actually. Let me use black. I want to reserve red for the final. Also black or something like this. So the estimates for the black data are going to be that. In general, they're going to be close, but not exactly the same, which means I can interpret those values here as values that a random variable takes. And this random variable that takes these values is what I call beta capital hat 0 or B0, beta capital hat 1. In general, it's a typical convention in many contexts, in many textbooks and publications. Random variables are usually uppercase. Values of random variables are lowercase. Okay, so these. Okay, so if then I have this random variable which takes values that are slightly different in every experiment, I can get a sense for what is the error I made in estimating these values in one experiment, in this experiment, for example. I can do this by defining the covariance matrix of this estimator. So let's understand this first element by element. Since now I have two parameters to estimate, I have two parameter estimators. One way to understand the spread of this beta 0 hat is by taking the variance of beta 0 hat, right? That gives me the spread of a random variable. You know this from your undergraduate statistics. And the same thing for beta hat 1. I can get the let me just use V, you understand, this is variance. The variance of beta hat 1, that gives me the spread. If I may write distributions, this is the distribution for the second one, this is the distribution for the first one, right? Okay. What do I know about these distributions? Well, we'll say a few things in a second. But in addition to these, because to these just the two individual variances, there is more here because these two random variables, beta 0, beta 1, may be related to each other. So if one goes above its typical real value, well, the other one, does it go also above its typical value? Could it be that it goes below the typical value most of the time? How does it do? Do the two vary in tandem or contrary to each other, or they are not related to each other? What captures that is what we call the covariance between beta hat 0 and beta hat 1. The covariance, it's the same thing, actually, I shouldn't write. It's the same thing. And this is what people call the covariance matrix, or sometimes it's called just the variance matrix for a vector. So it's the covariance matrix between, of the vector, rather, beta hat. Software computes that these days trivially. Mathematica, MATLAB, Python, you can get routines that compute this. And it's very useful for regression problems because you can get a sense of what is the error that you have in the individual elements. And in fact, it turns out that you can estimate those from the data. This is a fortuitous coincidence in the sense that the same equations, the same machinery that gives us an estimate of the values we are trying to estimate, the same equations that give us this, contain actually enough data in this matrix that give us an estimate for the covariance matrix. And this can be, so this is a definition, and this is a theorem now. There is a theorem that says the covariance matrix, I have, that's equation 28 in the notes. The variance, or sometimes, as I said, sometimes it's called just the variance of beta hat, because this is understood as a vector random variable. I explain this is by definition the vector beta capital hat. You can show that this is equal to sigma square of noise, the variance of noise, times this matrix X transpose X inverse. This is a famous matrix. It's so important that it's called the information matrix. In fact, frequently it's called the Fisher information matrix, because it was Sir Roland Fisher who introduced its great usefulness in estimating what mistakes we make if we try to estimate parameters. And in fact, he even solved the reverse problem. How do I design experiments to make this matrix, this information matrix large so that its inverse can be small, and I can have estimates of the parameters which are small. So this one big theorem, and in fact, if my model is correct, if my model structure is correct, that's where this is coming from. And there is an associated simple theorem also that says this theorem that we just showed, and I'll frame it because it's important. And it's the basis of most of experiment design. Come on. Let's see this. Sorry. Okay, this is as experiment. Of course, associated with that, I should have mentioned that first. If my model structure is correct, this straight line structure is correct, I can show that the estimates, somebody mentioned that already, the estimates of these parameters, beta 0 and beta 1, through this estimator that we defined here. Oh, this defines an estimator here because it gives you different estimates every time. So let's write it in general. The estimator is X transpose X times that vector beta hat is equal to X transpose Y. Then the expected value of beta hat through that, if the model structure is correct, is actually the true values of the vector beta. This is the true, the actual values. And this is a theorem again. It's a simple theorem to prove that. Question? No, just stretching. Okay. So this is the unbiased estimate. Those are general concepts in statistics. And what we mentioned already for the straight line can actually be generalized to practically all linear regression, as long as you have a problem that is of the form minimize a model that has the structure Y is equal to beta 0 plus beta 1, a function of X, plus beta 2 phi 2, another function of X, plus beta K function of X. So you have parameters beta 0, beta 1, all the way through beta 2, all the way through beta K. You try to minimize the sum of the squared errors. Well, try to minimize this with respect to the parameter vector beta prime, which means, let me write it more explicitly, sum of yi, I goes from 1 to p, the number of points, minus what the model spits out, squared. So this is beta prime 0 plus beta 1 phi 1 xi I at each point, plus beta k, phi k, xi. We try to minimize the sum of the squared errors with respect to the parameters beta 0, beta 1, all the way through beta k. It turns out you can write everything again as a vector matrix construct. So you have this minus that is the error vector. You need a matrix and you have the parameters here, beta prime 0, beta prime 1, all the way to beta prime k. And obviously here in the beginning you have 1, phi 1 of x1, all the way through phi k x1, going down 1, phi 1 xp, all the way phi k xp. Okay. And this dimension here is equal to this dimension. And that dimension here, of course, must be equal to this dimension here. So usually, typically, this is a tall and thin matrix. These are the parameters that need to be identified. And how do you minimize the sum of the squared errors? There is a theorem that says exactly the same. X transpose X beta hat is equal to X transpose Y. That's how you estimate the parameters. And the variance of the estimators, same way as before. It's this. And you may say, well, I don't know the variance of noise. Well, there are ways to estimate it from the data. I'll tell you in a second. Okay, again, let's make sure we understand the difference between this equation and that equation down here. This is an equation that is concerned with the estimator. This is a random variable. Why is this random? Because y is random here. This vector of measurements varies according to each experiment we do. For every set of p data points we do in the experiment, we'll get a different vector. In the same vectors x, exact values x1, x2, all the way through xp, the number of data points. Every time I solve this, I'll get a different solution. Every time I solve this, actually I'll do this. This is in our P. This is a random variable. And so is this, a random variable. This is a vector in our k plus 1. Okay, these variables are random variables. Okay, so that's covered in the notes on page 10. Let's move on, and page 11 for the generalization. It's the same ideas. And interestingly enough, you can now do these things for nonlinear regression. The reason why I digress quickly from linear to nonlinear is because nonlinear regression used to be a headache, I would say several decades ago. It's now trivial because computers can do it very, very easily. Not only is it trivial, it has taken off to new heights because practically all AI stuff that people do is nonlinear regression. Almost none of it is linear regression. Elements, internal elements may have linear calculations, but it's all nonlinear least squares. It can be done very, very easily and routinely. And for engineering applications that are not difficult, what does not difficult mean? You don't try to train a neural network that can tell a cat from a dog, or a catalyst that has been deactivated from an active catalyst by just taking images. You try simple things, such as fitting the response of a dynamic model. Well, that can be done easily. Example 5 does that. Let's see example 5. So this ties with what we learned in the early part of in the previous lecture, in the early part of the identification section. So we said if we have this input and we produce this output, and we make a step change here that produces something like that. The output asymptotically goes there. We can tell what is the response of the system. So if we have tau y prime of t plus y of t is k u of t, our famous first order system, extremely simple and all that. Well, this is the response. We never measure the response exactly. There are points that we take. So we have to draw the red line by taking these measurements and find the best values for this. The best values are tau. Okay. How can we do that? Well, there is a number of ways to do that. One way is to say, I will take all the measurements. So if this is x1, x2, all the way through xp, and I have the corresponding measurements y1 and y2 all the way through yp, I'll take my measurements, y1 through yp. I'll take what my model spits out. So how does my model spit out values here? Well, x here is time, right? So there are values here according to my model at time t1, given the parameters k and tau. I'll put this as semicolon to distinguish it from the parameters. Then model T P K prime tau prime. Bear with me for a moment so we can do this right. I promise you we're going to do this on the computer with enough data, which is on example 6. But let's start to understand first where this is coming from and what we are trying to do. So this is the model here. If I subtract one from the other, I get the error vector. This error vector has E1, E2, E3, all the way through EP. This minus that is the error vector, again, by definition. By definition, this is E1 through EP. And then I try to minimize the sum of the squared errors. Let me write it explicitly. So the sum of the squared errors is E1 squared plus EP squared. This is what I try to minimize. Minimize this by selecting values for k and tau. K and tau, right? Now, how the model functions can work in a number of ways. One is numerical. I take an equation solver. I write my own using Euler's method. I take MATLAB and put it there. My model spits out these numbers in a subroutine, in a function, whatever you call that piece of code. So it produces these things, the model at T1, model at TP. Construct Y1 minus model at T1, etc., YP model minus TP. Construct that, pass it to your minimization routine, done. So if you have software, it's very easy. You have a routine that solves the ODEs, that passes the solutions to an optimizer, which spits out the parameters k and tau. And it is done routinely these days. In fact, it's so simple you can even do it on Excel. It's not a big deal without using sophisticated software. MATLAB, of course, can do it routinely. Python can do it routinely. All software can do it routinely. In this particular case, because you have a simple model, what the model spits out is actually explicit because there is a solution to this equation. Within this input is a unit step change. And this is 1. We know the solution, right? The solution is analytical. When you start from a steady state, as I'm indicating here, right? Keeping things simple. So y at t is equal to, anybody remember what this function is? It's an exponential, right? What's this? So it's k minus e to the minus t over tau. t is time, which let me call it x so that all the points are, well, I'll call it t with the understanding that the points x refer to time. Okay, so this is, let's keep this as time. Next one is point in time 1, x2 point in time 2, and so forth. Okay, or let's call them time. Let me try to keep it as consistent. Let's see. Yeah, I think this is consistent enough. So that means then that the error is of the form y1 yp minus k1 minus t1, the first point over tau with a minus. They put the minus, yes. Keep going, prime, because I don't know these yet. 1 minus e to the minus tp tau prime. This. And now I want to find, this is the error, I want to find what minimizes the sum of the squared errors that I have here. So to minimize the sum of the squared errors, I goes from 1 to p minus k prime 1 minus e to the minus tau ti tau square with respect to k prime and tau. K prime. Very, let's do it together so we can visualize this after all this theory. So this is nonlinear. I'm not going to do a linear regression problem because you've done it a million times probably, so you know how to do that. Let's do this, which is slightly more interesting, so we can see what additional material one can also do. So I have here equation 42 that has the data in example 6 on page 14 of the notes. Let's try to see how I can use that so that we can visualize the whole thing. I don't need. Again, right on that. Yes. Okay, so this is on page 14, so let's go to 14. And it's these data I'm going to show you here. Okay, these data, so let me copy these data to Excel, so copy this to an Excel sheet. Let's start Excel. So we have, what do we have? We have K, so K capital. My estimate, I have tau, what I'm trying to estimate. Let me actually just make those hat and hat because that's what I'm going to try to estimate. So, hat, tau. Let's name these variables something. Oh, actually, I'll need, no, that's it, that's all. So Formulas, create selection, left column, and I have my X, which is, oops, um, paste it here somewhere. Hold on. It's a different way. Yes, safe. Mm, mm, Okay. I'll do it manually and avoid being overly sophisticated here. These are my data, my X data. So take these, Excel sheet. I'm pretty sure there are more efficient ways of doing that, but let's stick to that for now. And Y. So Y, I'm going to copy the data. Copy, paste. These are my Y data. Okay, very good, simple. This I don't need. What am I trying to do? I'm trying to estimate values for these two, right? So I have called this K hat, I've called this tau hat, give them something like 1.1.1, doesn't matter. I'll create the error. At this point, I have a measurement minus what the model predicts. The model predicts K hat multiplied by 1 minus the exponential minus this divided by tau hat. And close the parenthesis. This is my guess. So copy this down. And let's plot this stuff, by the way. So something like this. Let me actually make it a little more convenient so we can see how the model fits the data. So my model is going to be equal to K hat multiplied by 1 minus the exponential minus this divided by tau. Yeah. Okay, the error is equal to the measurement minus 1 more, right? So this is the error, and now I can have this extend that a little bit. Okay, so this is the model. I'll put a continuous line for the model. and with markers. And on the line, it's this. Okay, so this is the line. Clearly, it doesn't fit the data well because I started with something arbitrary. Um, I have the errors. I can construct the sum of the square errors. All of these. And I can try to minimize this. I could have done this by trial and error. So as you can say, I'll try something faster, 0.1 maybe. No, that's not the thing. 0.1, okay. This looks like, sorry, 0.5 maybe. Still not doing the job. Make this 5, oops, too much. You know where this is going, right? It's incredibly simple, so you can very quickly converge to this, maybe 2. This looks okay, but not quite. Could it be 1.8 maybe? Yeah, still not too happy because this doesn't look right. Instead of doing it this way, you just take the solver, so data, solver, you set your objective, which is going to be this, the sum of the squared errors, right? You want to minimize this by changing what cells you want this and that, these two cells. You don't care about positive, negative values. You want to do the minimization, solve. If I haven't screwed up anywhere, I'll keep the solution. Nice, beautiful, gives me nice results. Okay, so this is a case where nonlinear regression is nice, simple, it executes quite easily. Of course, you would like to ask yourself, do I trust this model? Is this a good model? Well, you always have to do checks when developing such models. Now, the checks that one simple check, and let me see how much I am measuring the notes. We don't have much space, but those are standard from regression. One check is to look at the errors, the residual errors, or sometimes just the residuals. So here, let me extend that. These are the errors here. Do they appear to be randomly scattered above and below 0? I don't see much of a pattern, right? Ideally, actually, it would be better to just have a separate plot. So I don't see anything of that nature. How about the R square? Well, the R square is simply the correlation coefficient. So between model and the measurement. So correlation between two arrays, this and that. That's the correlation. I need to square this. Of course, this is my R square. 99.7, that's, oops, did I square it? Okay, 99.4, and then realistically, like good R square. That simply says that my model fit is very, very good. That could be due to a very good model and a very good measuring device that gives me noise that is very small, but it doesn't say much about how good the model is outside this range. Models are good, especially nonlinear models are good for interpolation. I don't know what is happening outside. I suspect, based on fundamentals, that this model will predict also further down in time because there is fundamental structure in the model. It comes from this differential equation, and maybe the differential equation is second or even third order, or there are higher dynamics, but eventually, if it's a stable system, it will go to a steady state. This goes to steady state. I can trust this outside this range based on additional knowledge, not based on the R square. The R square simply says the blue dots and the orange line are very close to each other. Example 6 actually gives, just for historical interest mainly, and for one additional reason, which I mentioned in a second, it gives the Gauss-Newton algorithm, which takes this function that we have to use for my model output. What is this function? Well, let's do it here on the notes. Be specific. This is the right-hand side. What is this right-hand side? The k, et cetera, et cetera, et cetera. It's what I wrote down here. It's the set of model outputs. Model output is like this. The model output is explicit here. I don't need to use software integrator. So this model output is this, and we do the minimization. But it turns out, and you can use this in the Gauss-Newton method, which linearizes around the estimate at every iteration, and very quickly it goes boom, 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 and finds these estimates. Of course, the initial guess is important for any nonlinear regression problem. You see here convergence, you see here divergence. It depends on the initial guesses, right? Excel actually can be tricked with that. I'll show you in a second. But the important thing is that this can approximately be used as the information matrix. Why is this useful? Because it means now I can get the covariance matrix of parameter estimates, and I can get prediction errors, estimates of the errors in my predictions in the future, and all that. All that is a matter of statistics, and we don't have time to go over that in very much detail, but I'm giving you glimpses, and we'll see some of that as we do more examples, okay? So this is this example. Oh, let me convince you that Excel also would fail if you said the initial guess is -8 and -1. Let's see what Excel will predict. It predicts this stupid thing. So, well, stupid, it's just a figure of speech. Predicts disagreement between the model output and the data, right? And you see the error has a clear pattern and all that. Well, let's see what the solver does. So the solver, it's the same thing. If you ask it to solve, model says, yes, I converge to something that fits the data nicely. This is the least square solution. It's an optimum to which Excel converged, but it's because this regression problem is non-linear and has a number of optima. It's easy for the algorithm to be trapped. You see that it catches the trend nicely, except the residuals do have a pattern, or blue dots and orange line they have a pattern in what is left out. And the parameter estimates, you see that they're out of whack. They're unrealistic. So Excel can fail too. It's not that it doesn't fail. The thing though is that in most problems of this nature that you solve, you say, what the heck, this is a positive thing because I made a change in my input and the output went up. So the steady state again must be positive. So I'll choose what? A small number, let's say 0.1, not 100. 0.1. And the time constant, well, that's another positive number. So I would choose my initial guess like this. So still not very good in terms of my prediction, but now if I use the solver, well, I don't know what it's going to spit out, but I'm optimistic. Let's see. Sure enough, it converged nicely. Okay, because we were close enough to the optimum, and close enough to the optimum, every function is almost quadratic. You learned that probably in other contexts in your undergraduate courses in when you did oscillations in physics. Near the minimum energy, every oscillation is a perfect oscillation with second order ODE. Okay? So this stuff can be used now, like I said, more and more these days, this nonlinear regression idea. And the one key element here was that the model structure mattered. In what way did the model structure matter here? It mattered because A, we knew what to expect in the parameter signs. The gain is positive, the time constant is positive. So we'll use positive initial guesses. B, when we write model, we don't have to rely on software alone. We can rely on an explicit formula, which is not the norm, most of the time when we have nonlinear models, nonlinear effect of input and output, we don't have an explicit formula, but here we do. And because controllers use linearized models, which are approximately linear, we very frequently have such formulas. Okay, so it's for identifying models for control purposes, it's not uncommon to have a linear model. So we know the solution we can write. That's a nice thing, a nice feature. We can write a formula, don't have to rely on something that is a black box. At best, it will be, at worst, actually, it would be a gray box. Now, in the next subsection, which we'll cover after the exam, it's a subsection 2.4, we'll talk about the prediction error method. Let's introduce this topic here very quickly, and then, of course, we'll take a break so we can continue next time after we recap. So when we have here as an equation that is solvable and it gives us a nonlinear regression problem to solve, to estimate k and tau, can actually be looked upon in a different way. First of all, if we have problems like this, we typically identify models by taking computerized version of a problem, which means discrete time. And if we have an equation tau y prime of t plus y of t equals k u t, well, we can approximate this derivative at time k by this finite difference, and you know the notation now. K plus 1 means at the time point tk plus 1. So this is approximately equal to the derivative at time tk, which means this is approximately equal to tau y, well, k plus 1 minus yk over delta t is equal, plus yk is equal to k u sub k. And I can take yk plus 1 is approximately equal to yk plus delta t over tau yk, actually minus this on the right hand side, plus delta t over tau k uk, just the algebra. And I can write this in a more convenient way as yk plus 1 is equal to a yk plus b uk. I've done this before, right? We've done this before so we can see what this looks like. The interesting part is now people have developed a method that says, why don't I consider this to be a function of yk and uk and the parameters a and b? And why don't I create an error between this measurement and that output? So the model output will be ayk plus buk. And this I know exactly, it's what I throw in. Well, this I know with noise, but I'll pretend that it's okay. And it's now part of my model. And now this is what the model predicts. So I'm saying model, but this is not exact, it's measured, right? Very, very careful. This is exact. Well, again, to the extent I know my input exactly. And then I do minimization of the sum of the squared errors for all k going from 1 to p, the number of points or n. I try to minimize this with respect to a and b. I'll use primes because I don't know this. This is called the prediction error method. Why could this be preferable to what we did before with nonlinear regression? Because a regression here is linear. And when this method was developed, having a linear regression problem was a huge deal. So this has been developed to perfection. Now nonlinear regression methods are becoming more and more and more important, but this is still used quite a bit because it's extremely simple and easy. So we'll cover this after the exam. I'll stop here and we'll continue. We're going to have a review again on Wednesday and we'll continue. I'll hand out the exam in the end of the week and we'll continue on Monday. So. Close this. Save this. Stop sharing. And, oh, there was, oops. There's a chat. Same thing. Oh, thanks a lot. Okay. Anytime. And